So the only force acting on a 0.5 kilogram object as it moves along the x-axis is given by force is equal to 4x cubed newtons, where x is in meters. That means the 4 has to have units. What units does the 4 have? The whole equation has to give us units of newtons. This will be meters cubed. What do I have to multiply by meters cubed to get newtons? You're making it harder than it needs to be. I need to get rid of meters cubed, number one, right? How do you get rid of meters cubed? I need to end up with newtons.
Kilograms per
So what units does the 4 have to have?
Nobody told me there was any math.
Newtons over meters cubed. Okay, we got with that now. So the units of the 4 are newtons per meter cubed, so that once you multiply it by x cubed in meters, so meters cubed, you end up with newtons. Okay. So if the speed of our object at x equals 0 is 3.5 meters per second, what is its speed at 2 meters? So we have some sort of object at x equals 0, it's traveling at 3.5 meters per second. There's some sort of force acting on it. That force is varying with position. Once the box gets over here at 2 meters, we want to know how fast it's traveling. So energy. Energy is a fantastic way to go. Again, we can use work is equal to the change in potential energy plus the change in kinetic energy. Or all of our initial energy plus work is equal to all of our final energy. They're equivalent equations. So it doesn't really matter which one we use. In this particular example, though, what can you tell me about its potential energy of this system? It's not changing. So on a horizontal surface, so it's not raising in elevation. We don't know what's applying that force, but there's no additional spring. So delta U is 0. Or we can say U initial is the same as U final. So our equation simplifies a little bit. So work is going to be the change in kinetic energy, or the kinetic energy we start with plus whatever work is done is equal to the kinetic energy we end with. Either way. Work. How do we find the work done by a force if the force is not constant? Integrate. Work is the integral of force with respect to displacement. Your limits are your initial position to your final position. So the work done by this force is the integral of 4x cubed dx from our initial x is 0, our final x is 2 meters. So our 4 comes out, and remember we just said it has units of newtons per meter cubed. Integral of x cubed will be x to the 4th over 4. Plugging in our limits. Yeah, the 4's canceled. But we still have the 1 newtons per meter cubed. Those units don't cancel. X is 2 meters. Take that to the 4th power. Subtract, plugging in the lower limit, but the lower limit is 0. So 2 to the 4th is, what, 2, 8 times 2, 16? Units. Notice, we we had newtons over meters cubed on the floor. When we take this 2 meters to the 4th power, we have meters to the 4th. This gives us units of newtons times a meter, which is a joule. So doing the integral gives us the number of joules. In this case, the force is in the positive x direction, so we're getting a positive value for our work. The work is positive because this force is putting energy into our block. Now that we know the work, we can come back and plug it in either equation. If we plug it into this one, we have 1/2 mv initial squared plus the work that was done, the 16 joules, has to equal the final kinetic energy, so the 1/2 mv final squared. We're looking for v final, so we're going to divide by 1/2 m and take the square root. So 1/2, our mass was 0.5 kilograms. Our initial speed was 3.5 meters per second. Need to square that. Plus the 16 joules divided by the 1/2 of our mass. Square root of that is v final. Can you be able to plug it in? Let me know if you agree. You have 2.2?
8.73.
8.73 is what I got too. Okay. It's traveling faster now than it was at x equals 0. Does that make sense? Yeah, the force is getting bigger and bigger. The force is accelerating it, so it's speeding up. So basically, because that force was applied for those 2 meters, it put energy into the system, put energy into the block or box. The object, whatever the object was. The energy being put in makes it travel faster and faster. So please keep in mind, if force varies, which you'll know if it varies or not because you'll be given a function if it varies. So if you're given an equation for the force, then you need to integrate it with respect to position. When you integrate it with respect to position, that gives you the work. That tells you how much work that force did over that distance. Okay. Now with friction, for example, we haven't had to integrate with friction because the force of friction is constant. If the force is constant, it comes out of the integral sign. And integral of dx is just d, the distance that it travels.